In lecture 5, we are going to study vibrational transition. Okay, vibrational transition also affects the optical absorption. That's why we are studying the vibrational transition in addition to the rotational transition in the previous lecture. So first, let me remind you what is vibrational energy state. And as we studied, like for example, now if we have some diatomic molecules connected with a spring, and vibration is the vibrational oscillation of this molecule, right? So if this frequency is nu and 2 mu, so faster oscillation, 3 nu or something like this. So each of the atomic bond making oscillations, that's a different type of vibrational energy. So depending on the motion of the state of vibration, each molecules have a different energy of state, which is the vibrational energy state. And these different vibrational state can be transitioned by mostly infrared light. So now we are going to study the vibrational transition. Okay. So for example, here we just simply imagine that this distance is r, and if you take r in the horizontal axis and you take the potential energy of these molecules, and you can easily imagine that if the molecules are apart, away each other, the potential energy is going up. And also, if this one is approaching, too much approaching, again, this potential energy is going up suddenly. So this blue curve gives a real potential. But as a first approximation, when we obtain the vibrational energy for diatomic molecules, we make an assumption that this potential, especially we are interested in the potential somewhere around this region, meaning that there is some stable state equilibrium rated distance between two atoms, which is called RE. So here, so centered RE, it's like two mass are connected each other with a spring as oscillating. These potentials gives a parabola like potential, right? So what we usually assume as a first approximation, so that's B of X, or X is corresponds to R. So Bx equal B0 plus B, D, and then it is expanded was the distance, and D2B dx2 x squared plus, like this. And again, what we are interested in is not this constant value, and also we just ignore the linear term, and what we are interested in is this vibrational term, this like parabolic term, which correspond to this potential. So we just take this parabola part of the potential and solve the Schrödinger equation to obtain the energy of vibration. So what we can get is minus 2m f effective mass h bar squared d2 psi dx2 plus half d2b dx2 x squared psi equal e psi. And this m effective is simply sum of the two equal to the sum of the inverse of two masses. Right, and this is kind of the important concept of the mass. What it means is m effective. For example, if you think about, that in some cases one of them is very big and one of them is very small, for example, like this. In this case, the larger one, if m1, m2 case, m effective is simply like m2, one over m2 can be ignored, and then it's like m1. So m effective is almost like m1, which means this small mass is connected to the big wall, and then that's why this small mass is oscillating connected to the big guy, right? So it's just oscillating. So this what this effective mass means. Okay, and then also we assume that k equal this, that will be, and then the x2, which is obvious as spring constant, as something like this curvature of the parabolic. So after making, I don't know what is this. After making some calculation and a quantum chemistry calculation, you can check the quantum chemistry textbook, and you can calculate the energy of vibration, like V plus h bar omega, and this omega is given by k over m effective to the half, like this, and then V equal like 0 to the integer number. And so again, the energy of the vibration energy is quantized by the quantum number of V, and the unit of energy is given by h over omega, and omega is given by the k square root of the k over m, which is quite similar in the physics of the vibration of mass. So, and then by using the frequency unit, again using the GB in the unit of Kaiser, and to energy of the Joule to Kaiser, as we learned in the rotational transition, this Hc is a term of the Joule in energy in Joule. So by converting the energy to G, which is the energy unit in Kaiser, and we can write the energy of vibration as Gp equal plus half mu, and this mu is equal to h bar omega, and then the unit conversion Hc, and you can obtain 2 pi c over 1 and k over m effective half to the half, right? So like this. So from this Schrödinger equation and the consideration, we could now calculate the vibrational energy level. Okay. Then here's just some of the exercise, and please stop the video and then try to calculate the vibrational wave number for V equal 1 and 1. So the basic frequency of vibration, assuming the K value of those. Okay. Then here's some calculation, that just simple calculation, equal 2 pi c over 1 and k m effective over half, and m effective over 1 equal mh over 1 plus mcl over 1. And again, when the hydrogen is connected to chlorine, and it's almost like the chlorine is like a big wall, and then so it can be assumed like MH. Then the calculation is much simpler, and once it is to over 1 and 516 and 0.67 times 2 plus 27 and to the half. And now you can obtain the value about 295,000 per meter, which corresponds to about 3,000 Kaiser. So which is a typical value of the vibration of oscillation.